This video is about equations of motion for uniform acceleration, more commonly known as SUVAT equations. We will talk about the four most common SUVAT equations and the variables in these equations. We will solve a more straightforward example of uniform acceleration, and we will discuss another, a bit more complex example involving free fall, or in other words, acceleration due to gravity. Here are the four most commonly used SUVAT equations. You can find these equations in the IB Physics data booklet. There are 5 different variables in these equations: S, U, V, A, and T. This is why they are called SUVAT equations. S stands for distance or displacement, U for initial speed or velocity, V for final speed or velocity, A for acceleration, and T for the time taken to travel distance S. A quick side note here. You might have noticed that both in the formulae and in the variables table, the variables are written in italics. This convention in physics is used to make it easier to differentiate between letters that represent variables or quantities and those that represent units. For instance, when S is written in italics, it represents distance or displacement, and when it is not written in italics, it represents seconds, one of the units of time. Let's see how to use these SUVAT equations. In this example, a train starts from rest, accelerates at a constant rate, and reaches a speed of 45 meters per second while traveling a distance of 640 meters in a straight line. Based on this information, we have to find the acceleration of the train. It is stated in the question that the train accelerates at a constant rate. This is important because SUVAT equations can only be used when acceleration is constant, or in other words, uniform. This will not always be stated in questions, but in general you can assume uniform acceleration. The first step when solving a uniform acceleration question is to identify the variables that are given and the variable that we are looking for. Let's list the 5 variables: S, U, V, A, and T. The train travels a distance of 640 meters, so S is equal to 640. The train starts from rest, which means that the initial speed, U, is equal to 0. The train reaches a speed of 45 meters per second, so V is equal to 45 meters per second. We are asked to find the acceleration, and we do not have any information about the time. The next step is to figure out which equation to use. The equation we choose should include the 3 variables that are given in the question, so S, U, and V, and the variable that we are looking for, so A. The equation that includes all 4 variables is this one. Let's substitute. 45 squared is equal to 0 squared plus 2 times A times 640. 45 squared is 2025. 0 squared is just 0. So on the right hand side we get 1280A. Dividing by 1280 gives us approximately 1.6 meters per second squared for the acceleration. Notice that since both S and V are given to 2 significant figures, I rounded the acceleration to 2 significant figures as well. Let's see another situation involving uniform acceleration. In this example, we will work with free fall, which involves gravitational acceleration. Since gravitational acceleration is constant, we can use the SUVAT equations to solve this question. Let's start by identifying the SUVAT variables. The initial speed is 62 meters per second, so U is equal to 62. However, the other variables are not so obvious based on the information that we are given. Let's take a moment to think about them. We will start with acceleration. After the rocket is fired, it travels vertically upwards, slows down, reaches a maximum height, stops for a moment, and then falls back to the ground. We also know that air resistance is negligible. When an object is falling near the surface of the Earth, and we assume that air resistance is negligible, No matter what object it is, its acceleration will be approximately 9.81 meters per second squared. If you do not believe that this is true, and think that larger or heavier objects fall faster, drop a small stone and a bigger rock from the same height. Then observe which one reaches the ground first. You might ask, what if I drop a stone and a feather? The stone will surely reach the ground before the feather does. This is true, but only because of air resistance. To see a cool experiment about this, just type feather and bowling ball in vacuum into YouTube. But let's get back to our rocket. Throughout the entire flight of this rocket, the Earth exerts a gravitational force on it, which points towards the ground. Since this force is constant, the acceleration of the rocket is also constant, and its magnitude is equal to the value of the gravitational acceleration, which is taken to be 9.81 meters per second squared. There's no need to memorize this value, because it can be found in the fundamental constant section of the data booklet. The letter symbol for the gravitational acceleration is lowercase g. As a convention, on free fall questions, we usually take the upward direction as positive and the downward direction as negative. Since the direction of the gravitational force is towards the ground, the direction of the gravitational acceleration is also towards the ground, which means that it has a negative value. So to be absolutely correct, I will take A, the acceleration here, to be negative 9.81 meters per second squared. Let's continue with the other variables. As we said before, the rocket moves upwards, reaches its maximum height. At this point it stops for a moment, and then starts falling back towards the ground. Let's just focus on the first section of the motion, from the moment when the rocket is fired to the moment when it reaches its maximum height and stops for a moment. Since the rocket stops for a moment when it reaches this maximum height, its final speed, so v, is equal to 0. The maximum height reached by the rocket is basically the distance traveled, so in the first part of this question we are looking for s. Since we have u, v and a and we are looking for s, we will work with this equation. Substituting gives us 0 is equal to 62 squared plus 2 times negative 9.81 times s. Working a bit further and rearranging gives us 19.62 s equal to 3844. After dividing by 19.62, s is equal to approximately 196 meters. And since u is given to two significant figures, we can further round this to 200 meters. Next, let's find the time. Since now we have s, u, v and a, we can use any of the four equations that includes time. Let's use the first one. Substituting, we get 0 is equal to 62 plus negative 9.81 times t. When we rearrange, we get 9.81 t is equal to 62, and after dividing by 9.81, t is equal to approximately 6.3 seconds. This is the time it takes for the rocket to reach its maximum height, but we are looking for the time it takes for the rocket to fall back to the ground. Since the motion is symmetric, the rocket takes the same amount of time to go up and to come down. So to get the total time that the rocket spends in the air, we have to multiply 6.3 seconds by 2. So the time taken by the rocket to fall to the ground after it has been launched is 12.6 or approximately 13 seconds. Let's see what we have covered in this video. We started by looking at the 4 SUVAT equations that you can find in the IB Physics data booklet. We defined the 5 variables in these equations. We discussed that in order to apply these equations, acceleration must be uniform, or in other words, constant. Through an example, we saw that when solving acceleration questions, it is good practice to first identify the variables and then choose one of the 4 SUVAT equations to substitute. We discussed gravitational force and said that when an object is falling near the surface of the Earth, and we assume that air resistance is negligible, the acceleration of the object is 9.81 meters per second squared, which is the magnitude of the gravitational acceleration on Earth. We mentioned that the letter symbol for gravitational acceleration is lowercase g. We saw that on freefall questions, the upward direction is usually taken to be positive and the downward direction negative, which is why the gravitational acceleration is often given to be negative 9.81 meters per second squared. And in our second example, we saw that when an object is fired upwards and reaches its maximum height, it stops at this point for a moment before falling back towards the ground. Because of this, at this maximum height, speed is zero. This completes our discussion about equations of motion for uniform acceleration, or in other words, SUVAT equations. In the next video, we will discuss projectile motion.